Our featured presenter for this event is Joseph Ting, a product line manager of Yokogawa's high-frequency instruments. Joseph holds an electrical engineering degree from the University of Texas at Austin and has 15 years of experience in the test and measurement industry, including design and test capacities. Without further ado, I'd like to get started with the seminar by handing it over to Joseph.
All right, Sophia, thank you very much for the introduction, and thank you to everybody for joining this new seminar today. And over the next hour, this will be our first time giving this presentation on this subject, so certainly we welcome your feedback and comments and suggestions here at the end. The reason why I was motivated to take on a seminar on this topic is due to the fact that over the last 10 to 15 years of my career in measuring and instrumentation, I visit a lot of customers out there who have an electronics background, maybe an electrical engineering degree or an electronics degree, who were tasked to take physical measurements and work with mechanical objects. Or similarly, I've met mechanical engineers, people with mechanical backgrounds, who were tasked with taking electronic measurements or doing some electronic tests of a mechanical component. And the reality is there's not too many formal programs out there academically that train people on both electronics and mechanics, electromechanics, or as I'm going to call it, mechatronics. And so the people out there who have become expert at this have done so typically through experience. And so I'd like to share some of that experience with you guys today over the next hour. It's certainly a very large topic, and there's a lot to cover. That's why this seminar is designed to be 101. It's a basic overview of specifically the instrument side of considerations on how to take measurements in this area. All right, let's overview the outline here. I'm going to start off by talking about mechatronics versus electronics. And I struggled for a little bit about whether to use the term mechatronics or electromechanics, and decided to settle on mechatronics for a number of reasons, one of which it's actually just it's shorter and easier to write. But it seems to be a growing term. A lot of major manufacturers are using it, and it does describe what we're looking for. And I'm going to talk about, as I mentioned, the instrument side, how to find the right tool to test or design or validate or troubleshoot a mechatronics type of design project or test project. And then through the meat or the middle of the presentation, I'm going to talk to you guys about key considerations about channel count and sensors, sample rate, signal bandwidth, recording times and memory, signal conditioning, resolution and accuracy, and some on analysis as well. And then on the analysis side, I'll specifically talk about what kind of waveform characterization people do usually with measurements as far as looking at waveforms, scaling the sensor data, looking for anomalies, monitoring, and even automated tests. And at the end, I'll give you a broad overview of Yokogawa instruments, which are suited to mechatronics measurements. So let's start. As I mentioned, this is a very basic overview, and sometimes when I talk to people who are not in engineering fields, and they ask, well, what is an oscilloscope? What is a test and measurement instrument? The analogy I like to give is very simple, and everybody I think understands this. If you're trying to look inside of a biological system or a small cell or organism, what would you use? And the answer is very simple. Obviously, it's a microscope. Everybody knows that. This actually happens to be a confocal microscope made by another division of Yokogawa that lets our users look at live cells in 3D. And then similarly, we could say, all right, well, if you're designing an electronic circuit, maybe at the board level, if you're looking at chip-to-chip communication, or if you're looking at one board to another device type of communication, what would you use to look inside of the circuit and look at the behavior in there? And of course, the answer there is an oscilloscope. So those are the answers. They're very obvious in the case of a biological system and a purely electronic system. But with mechatronics, it's not so simple. Those of you who may have looked at the Wikipedia page for Mechatronics would have seen this diagram. I think it's a very clear diagram that explains what Mechatronics is. And in the beginning, I mentioned it's the intersection of electronic systems with mechanical systems, which is true. And sometimes people use that interchangeably with the term electromechanics. But Mechatronics is unique because it also includes control systems and computers. And specifically, all mechatronic systems will typically have a sensor or some kind of sensing front end, whether that's an automatic sensor or a user input or user control. And a mechatronic system will also have actuators. So whether that's visual or physical, oftentimes it's motors or something motorized. And in the middle, there will be a controller. So the controller nowadays typically would be a microcontroller or a DSP or maybe even FPGA type of algorithm or hardware, electronic hardware, interfacing a physical sensor or electronic sensor to a physical or electronic actuator. And as you can see in the black ring above, Mechatronics spans all fields, all vertical applications, from automotive to aerospace to medical to consumer products to manufacturing to industrial to so on. And obviously, if you're here, you already know what you're working on, but what you may not be aware of is, as I mentioned, Mechatronics is quite universal, and across the board, regardless of what field you're in, everybody's facing the same challenge, which is, as I'm working with my Mechatronics project, how do I put an instrument into this system? How do I monitor what's going on with my sensor activity? How do I monitor what's going on with my actuator activity? And how do I monitor what's going on with my controller activity? And relate all these things so that I can improve the design of my system. So if I were to take the same question to you and say, as I did with the biological system and the electrical system, now let's look at a mechatronic system, like a power tool or a vehicle or an industrial motor or a home appliance. What's the right tool to measure a mechatronic system or electromechanical system? And the answer, you can think about it for a second. My answer is, it depends. The answer is not quite so clear as it is with the other two. If you wanted to give a very broad answer, and if you forced me to give an answer, I would say, well, the right tool is some kind of voltage measuring instrument. Well, as it turns out, there are dozens of voltage measuring instruments and several types and families of voltage measuring instruments. So it really depends on what aspect of the mechatronic system you're looking to measure. And so depending on that aspect of the test, you may need multiple instruments. And that's what we've seen from our customer base often, is that they'll use multiple instruments to solve these testing requirements because the needs are so widespread. So what does it depend on? Well, that's what we're going to talk about here. Firstly, it depends on how many channels or sensors and sensor types do you need to measure. And I'll talk about this. I'll go into depth on each of these questions, and we'll take a look at those together. The next very important question is how fast are the signals? How fast are the signals moving? How fast do you need to look at the signals? There's obviously a wide range of instruments on the market that can measure from just a few times a second to billions of times a second and everything in between. How long do you need to record the signals, and when do you need to start recording? And mechatronic applications, more than any other type of applications, have a huge range. In one product, you may need to just test for a fraction of a second. In another product, you may need to monitor for several days. And sometimes you may want to do both types of testing at different phases in the design cycle for the same product. So it's important to understand what are your test requirements for length of recording, and how do you know when it's time to start recording. Okay, sensors, and I'll go into a little bit about sensors, but for the most part, this is not a sensors presentation. But we obviously have to know what kind of sensors we're working with. Do those sensors require some kind of signal conditioning? What is the desired accuracy and or resolution that you need to do the analysis? And speaking of analysis, what kind of analysis would you need to get out of the measurements? What kind of result do you need to make an informed decision about what to change in your design? So let's go into each of those questions one by one. How many sensors or channels do we need to measure? And what I've done is broadly listed typical channel counts for the most common types of instruments we see people using. On the low end is, of course, you could take a digital multimeter, benchtop or handheld, which would just have one or two channels and be a very simple interactive way to take a pretty low speed static type of reading. And of course on the right hand column you see sample rate, which varies depending on instrument too. We'll talk about that a little bit later. An oscilloscope, which to me is kind of like the hammer is to the carpenter. Almost every engineer out there has one in their office or in their lab. And so people tend to reach for the oscilloscope as one of the first instruments, if not the multimeter. And yet the oscilloscope only has 2 to 4 channels. So when we say how many channels do you need to measure, that means you can only look at 4 channels simultaneously at a time. And the reality is Mechatronic systems almost always have more than 4 channels. So can an oscilloscope solve the application? Sometimes yes, but in many cases the channel count is a little bit low. And moving on up to recorders or data acquisition type systems, paperless recorders, you can see channel count starts going up. There's a type of instrument I'll introduce you to called a scope quarter. That's kind of a hybrid instrument. But as you see, as your channel count goes up, typically your sample rate can go down as well. So that's something to be aware of as well. And as I mentioned, there's lots of instruments, benchtop and PC-based, on the market. And the channel count is relevant because it's one of the first, it's usually the first thing that you have to identify in your mind. All right, is 4 channels or even 8 channels or 16 channels going to be enough for the extent of the types of testing that I want to do? We see a lot of people out there working with 3-phase power for mechatronics applications. Maybe it's a 3-phase motor or a drive or inverter. And if you're looking at maybe an input and output, there's a 6-channel requirement right there. And so knowledge of that information will usually guide you in the first steps of choosing the right type of tool that you're going to need for your measurements. The next question is, how fast are the signals that you need to measure? And of course, the reason why we need to know this is because all modern test equipment use a digitizing technique. So they sample the data, and the data is sampled with a clock, and we need to figure out how close together that clock or the data points, the measurements need to be. We need to determine what's the maximum acceptable time resolution in order for you to accurately describe your signal or signals. So in terms of measurement speed, there's a couple terms here that are important. Sometimes you'll hear it talked about as bandwidth or sample rate. And when we talk about bandwidth, there's 2 types of bandwidth. There's the signal bandwidth, which is the highest frequency content of the signal that you're trying to measure. So again, your system may have many channels. Maybe it has dozens of channels. What we're interested in is the channel that's the highest speed or the highest bandwidth. What is its highest frequency content? If you were to look at its frequency domain information, and that's the signal bandwidth. We want to make sure that the instrument bandwidth, which is a specification of your measuring instrument, is higher than the signal bandwidth. Why? Because if it's not, then you'll effectively be blind to the higher frequency components. It's actually going to filter out those higher frequency components of your signal, and you won't be able to see those high frequency contents, regardless of how fast the sample rate is. So knowledge of your signal bandwidth is sort of the first step. That will help you lead you to finding an instrument that also has that minimum amount of bandwidth. And lastly, it will also help you determine what sample rate you need. Generally, mathematically speaking, your sample rate should be twice your signal bandwidth, but practically speaking, a good rule of thumb is that if your signal bandwidth is, let's say, 1 megahertz, then we advise that you apply a 10 times oversampling rule of thumb So you would want to sample at least 10 million samples a second to get all the 10 samples to redraw that each period of your signal. The other thing here that's noted in this slide is that generally instrument bandwidth really only becomes a concern above about 1 megahertz. So those of you who are dealing with measurements under about 1 million times a second or even 100,000 times a second, sometimes you don't even think about the term bandwidth. And that's because almost every instrument out there has more than about 100,000 or a million hertz of bandwidth. Every instrument can see that, so people don't think about it. If you're measuring very low speed signals like a thermocouple that only changes tens of times a second or 100 times a second, you never think about bandwidth. You only think about sample rate. But in my experience with Mechatronic systems, there's mechanical components which are typically slower, but there's also electronic components which can be much faster. And what we're interested in is the fastest component. What is its bandwidth, and what kind of instrument bandwidth you need to look at that. And as I mentioned before, once you have determined your signal bandwidth, it will lead you to what kind of minimum sample rate you will need to look at those signals. And similarly, you can infer what kind of sample rate you would need depending on the type of physical measurement or physical sensor that you're going to use. And I have a table here that shows physical sensors and the maximum sample rate that you'll usually see. And as I mentioned, the slowest ones will be things like temperature, humidity, or other static physical sensors. I very, very rarely, almost never see people measuring temperature more than 100 times a second. If somebody says, hey, I want to measure temperature at 1 million times a second, I would say that's overkill. And if an instrument advertises that it can do that, it's probably not telling the truth either. There's similarly, if you go up the speed curve, if you look at faster mechanical signals like shock and vibration or other mechanical sensors, the reality is mechanical sensors don't move that quickly compared to electronic signals. In fact, I would argue that nothing mechanical moves faster than about 5 megahertz. And so if you can think of any example that does, I would love to know, but in my experience, nothing mechanical. The fastest piezos in the world don't move faster than about 5 to 10 megahertz. And so you don't need more than tens of mega samples to measure those sensors. And similarly, if you're looking at other physical sensors, and the one I also want to call out here is if you're making RMS measurements or frequency measurements, if you're looking at maybe a tachometer encoder, that doesn't imply the frequency of the sensor itself, of the measurement of the sensor. It implies the frequency of your update rate. So how fast are we updating the frequency reading? How fast are we updating the encoder reading, and so forth. So those are the typical types of sample rates you might expect to need for those types of sensors. Okay, what happens when you don't have enough sample rate? I kind of described this already, but these pictures describe it a little bit more clearly. If you have the red original signal that's a moving physical sensor, and you want to capture it in your instrument, then the blue dots represent the sample rate. If your sample rate is fast enough, and here the sample rate looks to be about between 10 and 20 samples times oversampling, then we can easily recreate the signal by connecting the dots or doing some sort of interpolation. But if our sample rate is too low, as in the lower half of this slide indicates, and you try to reconnect the samples, then we get inaccurate signal reproduction. In fact, this is called aliasing, and we could go into depth on that, but the point is that there's some signal distortion and loss of information that you can never recover if you don't sample fast enough. So that's what happens when you don't pay attention to the sample rate being high enough. And what happens if you don't have enough bandwidth? So as I mentioned before, maybe your sample rate is very, very high, but you're using an instrument that has lower bandwidth than your signal bandwidth. Well, here's an example of a 1 megahertz square wave. And square waves, of course, have harmonics, higher frequency harmonics, odd harmonics. And if we have a 200 megahertz instrument, on the left side, we can easily recreate that square wave and all the detail inside of it. If we apply a filter at 1.28 megahertz, which is above the fundamental of the square wave, but below all the harmonic information, then that square wave gets distorted. So not having enough bandwidth will affect the signal shape, and it will actually create a filtering effect on your signal. So that's something to keep in mind. Another thing that people, this is especially important for mechatronics, but people don't really think about it much, is what happens when you have too much bandwidth or too much sample rate. And this is most common when people reach for the oscilloscope to take a mechanical measurement. Oscilloscopes, by nature, are very, very fast because they're designed to take pure electronic measurements. So a typical oscilloscope can sample at up to 10 gigasamples, 10 billion samples a second. And again, if you're looking at a mechanical sensor, as I mentioned, the fastest ones in the world may go at tens of megahertz. And so there's quite a lot of additional bandwidth, additional sample rate that you don't need. And what that creates is noise. It creates display noise. And it's the exact same effect as if you were to take a thermocouple and try to measure it at 1 million times a second. You don't need to. It's overkill, and it actually creates a lot of additional work and a lot of additional noise that may or may not be there. So the key here is to have enough bandwidth, but not too much bandwidth when you're looking at the measuring instrument. All right, moving on. Acquisition modes. Instruments out there, voltage measuring instruments and waveform measuring instruments typically have two ways to approach acquisition. Data acquisition and recording type of instruments usually employ a roll mode. And the roll mode is exactly like you see in the screenshot. The waveform will just travel from one side of the instrument to the other, and it lets you monitor low speed signals in a trend type of fashion. And usually because it's a lower speed application, you can just, it's a manual start and a manual stop. So you can press a physical button or click a mouse to start and stop it. That may be a few seconds of activity, maybe it's a few hours of activity, but that you'll see in a roll type of acquisition. Sometimes people call it a buffered acquisition or a free run acquisition. That's the effect. The other type of acquisition mode for sensor readings and mechatronics reading is triggered mode. And in Yokogawa instruments, triggered mode is anything under 1 second. So if it's 1 second or under, then our instruments automatically switch to this triggered mode, which will gather the data and display it on the screen. And it is usually designed for a single or a repetitive event. So if it's a repetitive signal, it will continually update the screen. If it's something that happens just once, like a startup or a shutdown sequence, then it will just update the screen just once, and you can monitor that information. And usually it involves a higher sample rate because it's a shorter event. Now, if you're in triggered mode, we need to know how to start that acquisition, because a manual start and stop will be really difficult to do if it's just a fraction of a second. So to try and manually start and stop and catch an event that's just say a tenth of a second by hand would be probably impossible or close to impossible. So these instruments will employ an electronic trigger, where the most common one, of course, you're going to set a simple edge trigger. But more importantly, you'll need to set a trigger position. And what the trigger position lets you do in a mechatronics application is it lets you look at more pre-trigger activity or more post-trigger activity. So let's say you're looking at a failure, you're expecting a failure, and you want to see all the events leading up to that failure. Well, then you'd set a late trigger point, like 80% or 90%, and you'd see mostly pre-triggered events that led to that failure. Let's say you're looking at a startup condition, so you energize a motor drive, and you want to watch it warm up. And you might set a pre-trigger, a trigger position of 10 or 20%, so you can see mostly what happened after the trigger. So that's what the trigger position tells you. And then you may say, well, what if I want to use both of these acquisition modes in combination, a roll mode plus a trigger mode? This is something that you don't see a lot on the market, but yet it should be, as far as I'm concerned, in every instrument that is designed for mechatronics, because mechatronics applications tend to need triggers, but they also tend to last for longer than a second. So having the ability to trend a signal for a long term, for longer than a second, maybe tens of seconds or minutes or even hours, but yet leave the instrument alone and stop automatically whenever it gets a trigger, that's a combination trigger, roll plus triggers. And common triggers that you might set, as I mentioned, an edge trigger is just a simple trigger that waits for a change in voltage or change in sensor amplitude. It could be from a low reading to a high reading, that's called a rise, or a high reading to a low reading, which is called a fall. Another common trigger that our users employ is called a timer trigger. So imagine where you set that timer to take a recording every hour or every minute for 60 minutes. Then you can capture a second every minute. That's something that's not very common in electrical systems, but it is quite useful in mechatronic systems, which tend to require longer-term observation. Pulse width trigger, and this is something that you will see on the electrical side. Everybody uses pulse width triggers, but yet it's actually pretty useful for mechatronics applications as well. So let's say you have a relay or a switch, or you have a connector, something that's kind of that can be an on state or an off state, and you want to trigger when it comes open or closed for longer than or shorter than a certain period of time. So that's what the pulse width trigger lets you do. And lastly, the combination triggers, which in our case we call them sequence triggers or triggers. You would describe an A condition and a B condition. So that may be a rising edge followed by a pulse width trigger, or a falling edge followed by a change in logic state. But the most common one that we see is an OR trigger, which is, as I mentioned, since mechanical systems tend to have many, many channels, maybe you want to monitor all 16 or all 32 channels, and if any of them rise above a certain level, that indicates a pressure problem or a load problem, and you want to trigger. So that's an OR trigger. And that's important that your instrument will be able to have the ability to do that. On the mechatronics side, many of our users are dealing with monitoring facility power. And by that I mean, if you're in the States, 120 volts AC, 60 hertz, and the corresponding voltage in your home country. And the reason why is that power is sometimes it's generated. If you're dealing with generators or transformers or solar or wind or hydro or some power generation. But on the utilization side, on the load side, it's also important to monitor because mechatronic devices tend to consume a lot more power than electrical devices. And so it's important to monitor that power supply. And a wave window trigger lets you define a golden waveform and a band, a percentage band. And any time that power supply fluctuates outside of that band, whether it's a spike or a dropout, or like you see some kind of distortion here in this example, then you'll want to catch that. And so that's kind of a long-term example, but you may have intermittent failure that doesn't happen very often, and you need to catch that electrically. So that's called a wave window trigger, and you'll see that in a few instruments. So we've talked about channel count. We've talked a little bit about sample rate, bandwidth. Now let's talk about how long do you need to monitor or record your event for. And that relates to memory length or record length, especially if your requirement for sample rate is higher. So what I've indicated in this table is the typical memory that you'll see on instruments. The fastest instruments, oscilloscopes that have gigahertz bandwidth and up, surprisingly, they only usually have about 10 million points or tens of millions of points of memory. And the memory specification, it tells you how long you can continuously store or capture points of voltage. Once you fill this up, you've got to clear it, and that means that you're blind or you have dead time, and you have to clear that information or save it before you can rearm and get more. And moving down, even if you're measuring at 100 million samples per second in a scope quarter, you get a lot more memory. You'll have 2 billion points of memory in this typically, but still it is a finite amount of memory. So it's relevant. I'm going to explain why here in the next slide. I would say under about 10,000 kilosamples per second, or maybe 100 kilosamples per second, depending on the instrument vendor. Sometimes at these lower speeds, the instrument will, rather than going to finite memory, it will go into some kind of buffered or streaming mode where you essentially have unlimited maximum memory. So it does vary from manufacturer to manufacturer where this unlimited memory starts to become limited. But especially I would say if you're dealing with measurements more than about 1 million times a second or a few 100,000 times a second, you really need to pay attention to if you're going to have enough memory to capture the observation period that you care about. Here's a slide that explains the concept behind that. It's very simple. Let's say you only have 5 points of memory. This is obviously exaggerated. But you have a waveform you need to measure. So you have to choose between spreading out those 5 points of finite memory across your observation period, or getting the higher speed sample rate that you want, but only maintaining that for a very short time. Here's a real-world example of what that might look like. The equation, the relationship between those 3 variables, memory, observation time, and sampling rate, is indicated in the top there. And it's basically to say that your memory constrains your sampling rate and your observation time. So for the same observation time, if you increase your memory, you increase your sample rate. So by increasing my memory 10 times, now my sample rate has gone up 10 times. When we go back, so you can see before and after. And this is for any observation time. So whether it's a second, a fraction of a second, or minutes, or hours, your memory is going to become important because it's going to control, it's going to affect how high of a sample rate you can maintain, and therefore it's going to affect how much detail you can see in your signal. Let's look at some actual numbers here. Mechatronic applications, as I'm indicating here, they often require higher sample rates for long observation periods. Why? Because if you have a slow sample rate, you may miss fast events like a noise spike. So let's say we want to acquire 30 days of data. This is a little bit extreme, but not uncommon. If you want to acquire 30 days of data at just 1 sample a second, you're going to need 2.6 million points of memory per channel or per sensor. And keep in mind that if each of those measurements is 16 bits, then that will be double that in terms of bytes. So you can expect about 6 megabytes per channel for 30 days at 1 sample a second. These numbers go up very quickly. Mechatronics measurements can easily go up to 100,000 samples per second, which now you're looking at 260 gigapoints or more than half a terabyte of data in order to maintain 100 kilosamples. So even though that's not beyond the storage capacity of hard drives, it becomes very cumbersome to go through that data and find what you're looking for and analyze it. Similarly, if you're looking at just 1 hour of data, but now our sample rate, let's look at between 100 kilosamples, or maybe you need a mega sample, 1 million samples a second to see some high frequency information over an hour. Well, that means per channel you would need 3.6 gigapoints. Or if it's at 100 megasamples per second, which is also not uncommon if you've got electrical activity in there, 360 gigapoints or 0.72 terabytes just for 1 hour of recording. So this is a problem. Mechatronic applications needing high sample rates for long observation periods. How do we solve that problem? The way that Yokogawa solves that problem is with something we call dual capture. And dual capture is essentially designed with an instrument architecture that employs 2 sample rates. It employs a low speed rate for continuous monitoring over the entire period, and then it employs a high speed sample rate for those transients. So we had already talked about trigger conditions. When those trigger conditions are met, the dual capture moves into the faster sample rate, captures a short window of activity, and then returns to the low sample rate. And here, in fact, I'm showing a screenshot of what results from a dual capture event may look like. Similar to dual capture, there's also something called memory segmentation, which can be useful in instruments. And what memory segmentation does is, rather than using the entire memory for a short burst of activity, it separates the memory into segments, like pages in a book. So if you have multiple triggers over time, you don't lose the past triggers. You don't just look at the most recent trigger. You can actually store pages of waveforms like pages in a book. And so instruments that support memory segmentation are especially useful when there's multiple triggers happening maybe intermittently over the course of a night when you're gone, maybe over the course of a month while you've got it in the field, or even in a lab kind of environment. All right, so we've talked a little bit about the instrument input side. Now let's talk a little bit about the sensor side. And this is obviously a very, very important aspect of mechatronics measurements. And as I mentioned, the purpose of this presentation is not to go into the sensor side. In fact, I know that for every sensor we could spend an hour or more talking about the technology and the considerations behind those. The fact is there are thousands of sensors types out there, and there continue to be new sensors that are invented all the time. But what these sensors do have in common is that they are all trying to convert physical measurements or electrical measurements into something that can be shared on one instrument platform and correlated with other sensors or analyzed. And in order to do that, those sensors sometimes require a little bit of massaging of their readings. And specifically, they may require amplification if it's a very low-level voltage, or attenuation. It may require conversion to voltage. Not all signals are voltages, and so they may need to be converted so that the instrument can understand it. And if there's circuitry in the sensor, it may require some power to activate those circuits. And the response of the sensor often is not linear, so either the sensor or some kind of hardware or software will need to linearize that before you can use that data in your instrument. So on the amplification side, you want to make sure that your instrument or your sensor can amplify that voltage. If it's a low-level voltage, such as line-level audio, maybe you're looking at millivolt type of information on there. Thermocouples are another example of very low voltage. On the other side, which is more common, I believe, in mechatronics, there's actually typically more high voltages than low voltages. And so when you're dealing with high voltages, the instrument or the front end of the instrument is going to need to accommodate for what can be hundreds or even thousands of volts directly into the instrument or with some kind of front end. An example would be a fuel cell stack. If you're talking about an automotive fuel cell stack, that's typically over about 500 or 600 volts. Not something that an oscilloscope or a pure electrical system can easily deal with. But in terms of amplification and attenuation, if you just look at the block diagram of the instrument that you're dealing with or the spec sheet, it will tell you what's the max and min input ranges. Or you'll see an attenuator or amplifier in its block diagram for each channel, which I have circled there. On top of signals being potentially large voltages or small voltages, another very important consideration for mechatronics measurements is when it comes to measuring floating circuits or isolation. And mechatronic measurements often contain common mode voltage. What is common mode voltage? It's essentially a voltage difference between your sensor ground and your instrument ground. And so if you look at this diagram here, we'll see the instrument on the right-hand side and a sensor on the left-hand side. This happens to be a Wheatstone bridge configuration. Maybe it's a strain gauge, and it's powered through voltage, constant voltage. But regardless, the power supply of the sensor and the sensor's ground may be different than the instrument's ground, and that's what's indicated in the bottom by the VCM or the common mode difference there. If there's any voltage difference between these 2 points, these 2 different grounds, then that means you have the potential for damaging your hardware, or you have the potential, best case scenario, you would create a ground loop. Worst case scenario, you would physically damage the hardware. So the unfortunate reality is mechanical systems most of the time do have a common mode voltage, and sensors are often floating. And when you put your sensor on top of something that has power or EMI or current flowing through it, you often introduce it to common mode voltage. So this is something that's especially important. How do we deal with it? There's a couple different ways to deal with it. The traditional method is to use a differential probe, and that a differential probe is a signal conditioning front end that essentially takes a differential measurement, and it provides a high impedance path between the plus and minus terminal to your instrument ground. So it solves the problem of this common mode voltage, and you'll find differential voltage probes that let you take readings, not only reject the common mode voltage, but can take very high voltage readings. In the case of Yokogawa, we offer one that does 1.4 kilovolts, another one at 7 kilovolts, and one at 30 kilovolts. So people who are looking for very high voltage measurements and isolation or differential measurements can solve it using that method. Another method that's gaining popularity is to use an instrument with isolated inputs. People don't usually think of this method because the first instrument they may have reached for, which is an oscilloscope, is not isolated. Oscilloscopes are not isolated because it prevents them from achieving the bandwidth that they need, and typically they don't need to be deal with pure electrical circuits. But mechanical or mechatronics applications do need this more often. So mechatronics type of instruments are starting to get designed with isolated inputs. And what that isolated input does is it's an internal design of a module or an instrument that provides an optical or a electrical isolation barrier separating the ground of the circuit or the sensor and the instrument. There is a benefit to this because you don't have the physical probe, as I showed in the front end, that's hanging off multiple channels potentially. You don't have to calibrate the front end separately. It's just a more convenient, simplified solution that a lot of customers are tending towards, and especially the newer types of isolated instruments can directly input up to 1,000 volts of isolation of voltage and isolate up to 1,000 volts of common mode. So those are the two methods. Though it's important to keep in mind that when you're dealing with an isolated instrument, now you have to consider the safety aspect of it because those common mode voltages can create a shock hazard. And so when you're shopping for isolated instruments, if this is something that you need, make sure that it's got an isolated connector in the front, which means it's typically a BNC electrically on the inside, but it has a plastic or isolated outer shell, as well as the probe side or the connector side. It should not be exposed metal because if there's common mode on that will ground through your hand as you connect it, and it will shock you and potentially hurt you. So both on the probe side as well as the ground clip, these are very important safety features if you're dealing with sensors or measurements that have common mode voltage that you will need to look for. Okay, so that's a little bit on the high voltage side and the sensor side. Very common for people in mechatronics applications to measure current. How do we measure current? And similarly, there's a couple different ways to do that. One method is to use a shunt resistor. And a shunt resistor is typically designed for low speed, high current type of measurement. And some instruments even include internal shunts, like power meters. You can employ an external shunt, though I would say it's probably a little bit less popular because you have to insert it in the loop, and the frequency response tends to be not quite as good, but with the right shunt, you can get very good precision. So there are pros and cons to shunt resistors. It's also worth mentioning that the 4 to 20 milliamp current loop has been a standard for decades in the industrial side and in certain aspects of the mechatronic side, and instruments can be designed to support those internally with an internal shunt designed for this standard, or a precision resistor shunt resistor can be applied to the front end of that terminal to achieve the same effect. The second method to measure current, which is quite popular, is by using a current probe. And current probes are usually clamp-on, but they can be through-hole. And these clamp-on current probes are usually designated by either AC, if you're only looking to measure AC content, or AC plus DC content. So maybe you have some DC offset or some DC current that you're looking to measure. And these probe technologies exist. They're very easy to use. They are active, so they will typically require a battery or power supply or some active supply from the instrument. But they make current measurements pretty easy and to get into your instrument in combination with the voltages and the other sensors. Another common type of measurement in mechatronics is power. How do we measure power? The easiest way to do it and the best way to do it is with a power meter or in power input module that is designed to directly measure power. And what do I mean by that? You want to measure watts, you want to measure power factor, you want to measure apparent power, real power, power consumption, watt hours. The other method is to do so using a current probe with real-time user-defined math. And similar to the power meter, to measure power, you're going to need to measure voltage and current, and then you're going to need to do some calculations internally to the instrument to arrive at the real power, the instantaneous power or the power factor. So these are the two different ways to do it that are recommended by us. Other sensors. Okay, obviously, as I mentioned, there are thousands of sensors out there. The most common ones I have listed here below. Generally speaking, as you have seen with both the current and the power measurement, your choices are to use an external signal conditioner or transducer or circuit that converts it into a voltage and then brings it into your voltage measuring instrument, or to utilize an instrument that takes into account the special needs or conditioning of these sensors, whether it's a direct RMS measurement or frequency measurement or accelerometer or strain or thermocouple, and takes care of that signal conditioning for you inside of the instrument itself. Usually when the instrument does that, and even when it doesn't, a mechatronic design instrument should support scaling, because at the end of the day, if you're measuring PSI or degrees, it's no use to you if your instrument is showing you voltage. So you're going to need to scale that. And the instrument should have a menu similar to this that allows you to do a 2-point scaling or MX or AX plus B type of scaling, as well as use the appropriate engineering units and maybe trace labels and other user interface types of things. They're labels showing you logically what you're looking at. So that's just something to keep in mind there. So we talked a little bit about the time axis, the sensors. Let's talk about vertical resolution. What is the desired resolution and accuracy? And if you've been using instruments for a long time, I'm sure you'll know that instruments are classified by bit resolution. And bit resolution tells you how many voltage levels the instrument can quantify. And the simple formula is 2 to the number of bits, with the smallest voltage change being resolved as an LSB. And this is an exaggerated example. Well, it's a real example, but I've zoomed into a ripple on top of a DC offset to show you a worst-case scenario of 8-bit measurement versus a 12-bit measurement versus a 16-bit measurement. And so the message here is mechatronics oftentimes involve very wide dynamic ranges, meaning your sensor may be static for a while or at the very low level, and then it's going to change all the way to the extreme. And when it changes to the extreme, it will have some fluctuation around the extreme state, and you want to capture that. And so it's especially important that the instrument has enough bit resolution to capture this wider dynamic range than you'll typically see in a pure electrical circuit. So look for 12-bit or a 16-bit solution as opposed to an 8-bit. Now we're going to switch gears into measurement and analysis. What kind of analysis are you looking to get out of the measurement? Our customers usually look for one of two different types of displays. They'll usually look for, if they're dealing with slow signals, a license tag or numeric kind of view or a bird's eye view of what is the current DC measurement of all of my channels. And if they're not looking at that, maybe they want to look at the waveform amplitude versus time, like a graphing instrument. And so these are the two types of views that in the past you may have had to reach for two different types of instruments, a recorder and an oscilloscope. To solve that, wouldn't it be nice if you could do that in the same instrument? If you're looking at the waveforms, you may expect to do extract some calculations on there, like cursor measurements, things that you'll find in an oscilloscope. Being able to look at X and Y positions, and being able to take parameter measurements, like automatically measure the frequency or automatically count the number of pulses in a stepper motor rotation or something like that. And to do those calculations automatically in the instrument rather than having to do it by hand, or rather than having to download it and do it in Excel or in MATLAB or in some custom language. Being able to do that in the instrument automatically like an oscilloscope is useful. Advanced parameter analysis is trending and showing the same analysis results in a histogram or maybe in a trend. So maybe you want to trend the rise time of the signal or trend the peak-to-peak voltage of your sensor over time as environmental conditions change. Or even creating your own user-defined map. And we see the user-defined map being used a lot with respect to physical sensors because the relationship between displacement, velocity, and acceleration is simply the integration or the derivative. So simply by taking a position sensor, such as a tachometer or encoder, or LVDT, or a potentiometer, and you can take the derivative of that to get the velocity, linear velocity or angular velocity, and then take the derivative of that again to get acceleration. And similarly, you can take an accelerometer, which measures acceleration, and integrate that and take out the DC offset, and now you've got velocity, and double integrate it to get position. So things like that you can do with user-defined math, as well as making calculations for power if you have a current probe. Advanced calculations like XY display mode and fast Fourier transforms. These are all oscilloscope type functions that are actually pretty useful for Mechatronics type of applications. Looking at the frequency domain response of an accelerometer is very useful. Vibration and looking for resonance and looking for frequency spikes is very important in mechanical systems. And I don't want to neglect logic. Logic is also very important. There's very few systems out there, mechatronic or electronic, which don't include some kind of digital control circuitry. And whether that digital circuitry is pure electronic, like a TTL level, like a 0 to 5 volt, or maybe it's an industrial, such as a contact closure or a relay. These are things that are important to bring into your measurement system and synchronize it and correlate it with the physical sensors. So it's important that your instrument can do that. And lastly, as you move from the design validation and test to the manufacturing process, you may want to scale these measurements up in terms of performance, in terms of deployment, in terms of speed. And there's automated software packages that can help you do that with the help of an integrator or programmer. And so it's important that the same instrument or some variant of that instrument does support those interfaces. So I'm going to go back to the same question I asked you in the beginning, and hopefully you feel a little bit more educated now after about an hour of going through this. And I'm going to say, what is the right tool to measure an electromechanical system? Maybe the answer is still not completely clear. Here we have still another vehicle, an industrial motor, household appliance, vacuum cleaner there, some industrial lighting, some power tools there at DeWalt. How do we measure those? What's the right tool? I would say that really in an ideal world, you would want some combination of an oscilloscope and a recorder or data acquisition. There are things that we've discussed through the course of this presentation that are useful from both of these types of instruments. Specifically, we'd like to have the wide bandwidth of an oscilloscope. We'd like to have fast sampling speed. We'd really like to have super long memory so that we can take advantage of those long observation periods. We'd like to have great vertical resolution for the dynamic range. We'd like to support lots of input channels of different types of sensors, but yet we'd like to keep the triggering and analysis of an oscilloscope. So how do we accomplish that with an oscilloscope or recorder? The answer is, unfortunately, you really can't, and that's why Yokogawa has, starting about 20 years ago, designed a platform that is targeted for mechatronics, and that is what we call Scope Quarter. And Scope Quarter is a platform that is modular. It takes the features of an oscilloscope and it takes the features of a recorder or data acquisition system and puts it all together. We call it the Swiss Army knife of measurement tools because we realize the demands of mechatronics measurements are so high. The Scope Quarter is designed to be the tool that you need at that appropriate moment, whether it's a fraction of a second measurement or a 30-day measurement, whether it's a microvolt reading or a kilovolt reading, whether it's 2 channels or 128 channels. And that's the nature of mechatronics, is it can be so demanding and so specific depending on your application. And the current generation from Scope Quarter from Yokogawa is what we call the DL850. I'm going to switch into some product introductions now for the last few minutes. This product we just released a few months ago, and it's already won the Best of Sensors Gold Award in Chicago just a few months ago. And as I mentioned, it is very versatile. Versatile is the name of this instrument, and it is designed for mechatronics. And you'll have this presentation so you can see the list of sensors and modules that it supports on this platform. We make a version called Scope Quarter Lite, and this version is designed for ease of use, technician type of interface. In fact, it has a wide printer on the output, so people can carry, can trend over time or take printouts with them as they go. And as I mentioned, if you take a broad look at data recorders or data acquisition and oscilloscopes, they're also things that the Scope Quarter can't always do. Scope Quarters your application may need more than 128 channels, or maybe it needs more than a few hundred megahertz. And in those cases, you will still need to lean towards a data acquisition type of tool or an oscilloscope. And in those cases, Yokogawa also makes data acquisition and oscilloscopes, and I've just very briefly showing you here our high-speed data acquisition tools, SL1000 and WE7000, and low-speed data acquisition tools, which have a PC-based and standalone benchtop type of version, as well as oscilloscope families that reach into the 10 gigasample and 1.5 gigahertz bandwidth ranges with mixed signal logic type of inputs. And these scopes are very useful for debugging the controller aspect of your mechatronic system. Maybe it's got some SPI or I2C or CAN bus on it, and these instruments often are very complementary on the electronic side or the low speed to high channel count side. So to summarize, we covered electronics versus mechatronics, some key considerations for mechatronics that are unique to those types of measurements. We talked about the types of analysis that you might wish to do, and then I introduced the Yokogawa instruments. So with that, the last thing I'd like to say is that we do have application engineers on staff to consult with you at any time. If you do have a particularly challenging application or measurement you're trying to do, please give us a call. We'd be happy to talk to you and help you, guide you in the right direction, whether the solution is from Yokogawa or someone else. And our website has really good content as well as far as product information, seminars like this one, but on other topics which are recorded, application notes, and recordings of videos. So I welcome you to visit our website and contact us if you have any other further questions.
Thank you, Joseph, for a wonderful presentation. We have run out of time for our Q&A section, but please be assured that if you submit a question, they will be answered via an email. Also, if you have not yet answered the poll questions, I would request you to please do so at this time. Just as a reminder, we did record this webinar, and it will be available for you in archive form 24 to 48 hours from now. I will be sending a link, an email to everybody with the link included, and also for you to download the presentation. Thank you once again, and we hope to see you online at our future web seminars.